There is a structure vaster than anything the human mind was built to grasp, an invisible lattice of filaments and voids stretching across billions of light years, and you are standing inside it right now without ever knowing it was there, born from microscopic ripples in the fabric of a newborn universe, amplified by an unseen scaffolding we call dark matter. This cosmic architecture quietly dictated where every galaxy, star, and planet would ever come to exist. This is the story of how scientists learned to map the unmappable, to trace the fingerprints of something that cannot be seen but shapes everything that can, revealing that our entire galaxy is nothing more than a single glowing thread in a web that holds the universe together. 400,000 years after the Big Bang, the universe was almost perfectly smooth, a glowing fog of plasma stretched across all of space, uniform to 1 part in 100,000. That tiny fraction, those faint quantum ripples imprinted in the density of the infant cosmos, would become the seed of everything that exists today. Every galaxy, every star, every planet capable of holding a curious species who would one day look up and ask what any of it means, traces back to those microscopic imperfections in a plasma so hot that atoms themselves could not yet form. For hundreds of millions of years, gravity worked in near silence on those faint irregularities. Regions with slightly more matter pulled harder on their surroundings, drawing in more material, growing denser still, while regions with slightly less matter thinned out even further, expanding into emptiness. It was a slow, patient sculpting process. Matter creeping across space at a pace that defies human intuition, gradually organizing into faint thread-like patterns. Cosmological simulations that model this era show particles flowing like smoke caught in a draft, streaming along invisible currents, gathering into filaments long before anything resembling a galaxy existed. What actually drove this process was something ordinary matter alone could never have accomplished fast enough. Dark matter, invisible and unaffected by radiation pressure, collapsed first, while ordinary gas and light were still locked in a hot, turbulent embrace. Dark matter had already begun forming clumps and filaments, an unseen skeleton stretching across the cosmos. It did not shine. It did not interact with light, and yet it dictated where everything visible would eventually go. Astronomers estimate dark matter outweighs ordinary matter by more than 5 to 1, meaning the visible universe we study is essentially decoration on a much larger, invisible frame. Ordinary matter followed dark matter's lead. Gas, cooling and thinning as the universe expanded, fell into the deep gravitational wells that dark matter had already carved out. Inside those wells, densities climbed high enough to trigger nuclear fusion, and the first stars flared to life, some of them hundreds of times more massive than our sun, and burning through their fuel in a few million years. Clusters of these stars became the first galaxies, strung out along the dark matter filaments like beads of light suspended on threads, too faint to see directly, yet powerful enough to shape the destiny of everything nearby. As billions of years passed, gravity kept building on itself. Galaxies drew closer to their neighbors along the same filaments that birthed them, merging into groups, then into galaxy clusters containing hundreds or even thousands of galaxies bound together by gravity. These clusters linked to other clusters through even larger filaments, forming superclusters that stretch for hundreds of millions of light years, structures so vast that light itself takes hundreds of millions of years just to cross them. Between these filaments lie cosmic voids, regions so empty that the density of matter inside them can be a tenth or less of the universal average. Vast dark gaps carved out by the very gravity that built the bright structures surrounding them. Step back far enough, and a pattern emerges that looks almost organic, resembling a sponge or a neural network more than anything built from cold physics. This is the cosmic web, the largest known structure in existence, a lattice of galaxies, gas, and invisible dark matter spanning the observable universe. It did not appear suddenly. It grew, thread by thread, clump by clump, over nearly 14 billion years, and understanding how it formed is the first step toward understanding everything held within it. The first hints of this architecture were not visible to any telescope, but emerged instead from banks of supercomputers, decades before astronomers could map the real thing with confidence. In the 1980s and 90s, cosmologists began running simulations that treated the early universe as a sea of particles governed by gravity alone, watching on screen as random fluctuations pulled matter into strands and knots that bore an uncanny resemblance to what surveys would later reveal in the actual sky. The Millennium simulation, completed in 2005, tracked over 10 billion particles of dark matter across a volume of space more than 2 billion light-years wide. And when researchers compared its output to real galaxy catalogs, the match was startling. Filaments appeared in the same rough shapes, voids opened in similar places, and the general skeleton of the cosmos, invisible and mathematical as it was, looked like a blueprint the real universe had somehow already been building. Sky surveys soon caught up to the simulations. The Sloan Digital Sky Survey, mapping the positions of hundreds of thousands of galaxies, revealed structures like the Sloan Great Wall, a filament of galaxies so long it stretches across more than 1 billion light-years, dwarfing anything astronomers had imagined possible just decades earlier. Nearby, astronomers charted the Buddhist Void, a bubble of emptiness nearly 250 million light-years across, containing so few galaxies that early observers wondered if their instruments had simply failed to detect anything there at all. These are not anomalies. They are simply the largest visible threads and gaps in a pattern that repeats itself at smaller and smaller scales throughout the observable universe, right down to the local group of galaxies that includes our own Milky Way, itself just one bright knot, clinging to a minor filament in an unfathomably larger design. Turning theory into a map required astronomers to measure light. Every galaxy's light stretches as the universe expands, a redshift that reveals both motion and distance, combined with position on the sky. This lets researchers plot a galaxy's true location in 3 dimensions rather than the flat view we get from Earth. The Sloan Digital Sky Survey did this for hundreds of thousands of galaxies, and later surveys pushed that number into the millions, each point adding to a growing map. What emerges is startling: a glowing lattice of filaments and walls curling around vast dark voids, the same pattern old computer simulations had predicted decades before telescopes could confirm it. But redshift surveys only show where light is. To find what cannot be seen, astronomers rely on gravitational lensing, where the mass of unseen dark matter bends and distorts light from galaxies behind it. A distant galaxy's image might smear into a faint arc, and by measuring that distortion, scientists calculate the mass and shape of the invisible material causing it. Clusters like Abell 1689 are famous for this, their gravity-warping background galaxies into arcs that map dark matter with striking precision. Motion offers a second clue. Galaxies within clusters move too quickly to be held together by visible matter alone. Without an unseen source of gravity, they should fly apart, yet they remain bound, as though wrapped in scaffolding no telescope can directly detect. Layered together, redshift maps, lensing distortions, and galactic motion consistently point toward the same invisible framework, a structure felt only through its gravitational fingerprints. What that structure truly is remains unresolved, and within it, our own Milky Way sits quietly, one luminous thread woven into a cosmic web spanning billions of light-years. To stand at its edge and look outward is to peer into a filament of that same web, stretching toward neighbors like Andromeda, pulled along the same invisible architecture. Cosmologists often compare the large-scale structure to a sponge, with filaments and clusters forming walls and voids carving out empty chambers between them. Along the filaments, matter and dark matter clump together, giving rise to the galaxies we see. Simulations like the landmark Millennium simulation recreate this web from the ground up, starting with density fluctuations left over from the Big Bang and evolving them through billions of years of gravitational collapse. The structures they produce mirror what surveys like Sloan actually observe, suggesting the same unseen substance has quietly directed cosmic structure since the universe was young. Yet dark matter has never been directly detected. No collider has isolated it. No underground experiment has captured a definitive signal. Candidates range from weakly interacting massive particles to axions, while some physicists propose modifying gravity itself. But every such alternative falls short against the full weight of evidence, from lensing to the cosmic microwave background.